Hello everyone, welcome back to the session. So yeah, in this third session today we'll be discussing about we'll be implementing basically what we have learned in the theory session in the morning. Okay. So yeah, like as yesterday we'll be quickly going through the like a quick implementation of the classifier kNN today, just like we have learned a naive based classifier yesterday. So yeah, as usually, let's import all the required libraries and packages. So yeah, so like yesterday we have worked on the iris dataset, right? Like if you look at the dataset, like we have got four features, right? All sepal lengths and widths and petal length and widths, right? So yeah, I mean let's actually have a quick recap at the dataset again. So the dataset size is 50, and with three classes in the dataset, right? So yeah, we shall be using the same iris dataset again today for performing kNN like kNN classifier. So let's pull our dataset into our local repository. So if you see now, on the left panel we have got our iris data in the CSV format and our input image. I mean the sample image for the inputs, right? So yeah, so now the next step would be reading our dataset as a data frame, right? So you have already you have been introduced to the pandas data frame. So we using that we shall read our dataset, your CSV file into a dataset variable. Fine. So now let's see what is inside this dataset as usually. So let's look at the first five samples. So if you see, we have got the same thing, right? Our four features and our label. I mean the class outputs. All the values to be predicted, right? The class, we can say what the ground truths actually. So again, let's have just have a quick look at the like the sample images of the three classes. Okay, like we have done yesterday. Iris types. Seems to be an error with the file we pulled. Let's again re-download the file and let's upload. Yeah, this works now. So you can see, right? I mean, like all the three classes. I mean, all the three flowers will look very similar of three different classes, right? So just like this is sample image, and then let's go to the next step in our implementation part. So let's basically get our train well. I mean the x variable and the y variables. You can say, right? I mean x is our future vector and y is basically our the class labels or the obviously y is the class label here, and we'll be using x. I mean using a x data frame. I mean all the four feature vectors will be predicting a particular. Will be predicting a particular class of it, right? So let's do that. So now let's basically go print and check what is inside x and y. Fine. Well, let's do this for a even better visualization. Okay. So so if you see this, our feature vector now has got only the four features. I mean, of the data set, right? I mean, all the sepal lengths, widths, and petal lengths and widths. So using these four values, we will be predicting the class output, like whether it is setosa or versicolor or vagnica, like that, right? So similarly, if you look at our y values, we'll be having a corresponding class labels for each input. Like you can see, right, like all the class outputs. Yeah, but these are actually string values, no? So we should be like we discussed yesterday, we should be doing what, converting them into numerical values, right? Like either one hot encoding or numerical encoding, that's up to us. Fine. I hope this part is clear. So let's remove this unwanted cell. So now we have split our data set as our x data set and the, I mean, x variable and the y, the labels of the data set, right? So now let's split our data set into test and train subsets. Okay. So obviously, the ideal practice or the regular practice, let's have a 80-20 split. So we'll be having a 20% in our test size. Okay. I mean, in a test set, So your random state can be any random value, or the regular or the widely used value is 42. Let's stick to that again. So now we have got our x train and test values, I mean test sets ready with our corresponding labels. So again, now let's actually visualize what is inside both of them. So if you look at this, x train is an numpy array with, like, each array contains a list, or again an array of containing four attributes, right? Or the four parameters, or the four features. Like each of them corresponds to a feature vector, right? Or we can do this. So for the first feature vector, the corresponding label would be setosa. That's all. We have actually divided the entire data set into two parts. One is x train, or the x variable, and the y part, right? Makes sense, right? So similarly, if you again try printing x test and y test, you'll be getting something like this. Okay, the similar kind of thing. So now let's actually perform feature scaling. I mean, you have heard what feature scaling is. So we'll be basically normalizing our values into a particular range. Basically, we are applying z-score normalization here. So you might be aware of this z-score normalization. So what is z-score normalization? For a variable x, we take, like, we x norm, or the normalized form of the input is basically x minus mean, right? X minus mu or mean, the mean of the variable, divided by its standard deviation, right? I mean, just for our like a quick recap on the z-score normalization. Or basically, we call this standard scalar or standard normalization because we'll be bringing that into a Gaussian distribution finally, like standard normal distribution, right? With the standard deviation as 1, and the for the zero mean data, obviously the mean would be 0, right, after normalization. So that's what where this name has come, standard scalar or the standard normalization. So after normalizing the data, see, even without normalizing, your classifier would work. But the reason for normalization is to make our model converge faster. I mean, after with less number of epochs or iterations, the model will converge. That's a benefit. That's it. So no big algorithm and logic here. Just to make our model converge faster. That's it. So I think you might be remembering this part. This thing we have discussed yesterday, like the naive-Bayes classifier. So again, now let's go to the second part, which is like the one we have seen in theory part today, the kNN classifier. So So again, let's take we'll be actually importing a kNN classifier. I mean the k neighbors classifier. Like we are actually importing it from the scikit-learn package. Okay. So we'll be let's assign our neighbors as 5, and then train the model on the training data. Fine. So you can see after this function, classifier is like an ADT here, right? So I mean this variable, so we are importing this particular method from the sklearn package, and we are actually assigning it to a classifier ADT. It's like an ADT. So this ADT dot fit, so this ADT contains lots of functions. So we actually perform the fit method, which basically trains the model on the given input data with corresponding labels, right? So yeah, let's do it again. So now, so as you have seen earlier, our test data is also ready. Now, then again, we'll use this predict method on the classifier ADT. I mean, ADT is like a abstract data type, right? It has got data with it, and or you'll be basically providing the data, and it has also got its corresponding built-in functions, right? So classifier dot predict. Let's get all the predictions for the testing data. So now actually let's look at what is actually inside the test data. I mean, what is the class distribution inside the test data just for our confirmation. So like, we should make sure that at least one sample from each class is inside the testing data set, right? So if you see, the inside the testing data, in y underscore test, if we apply this method, unique method, you know with a variable return count which is initialized to true, which is set to true, in that case we'll be getting the counts of unique values inside of that. I mean, if you look at y underscore test, what are our labels? Setosa, versicolor, and virginica, right? So if you see, there are 10 samples corresponding to setosa, 9 and again 11 respectively corresponding to class 2 and class 3, right? I mean, just for our visualization, that's it. Nothing, no, no, not a big deal in this case. So again, I mean, as we have already performed prediction operation, now let's see, let's analyze the performance of the model. Let's draw the confusion matrix for the particular. I mean, we have got our test and prediction values ready, right? So we'll be again, from this scikit-learn dot metrics. So scikit-learn is a package, and there is a sub package inside that which is metrics, and from that we're actually importing this method, confusion matrix, or this function or method, whatever. So we'll be passing our variables, which is our predicted values, and the labels or the ground truth values, right? Makes sense. You can just look what is inside the prediction values or the ground truth values, let's see. So if you see this, both of them, if you look, the first one is matching. I mean, like we can actually say if there are mismatchings, that would actually correspond to the error part, right? So if we see, only the diagonal elements are completely full, meaning the model has achieved 100% accuracy, right? I mean, this is a small data set, so obviously we would be getting optimum, like the state of the art performance. But just for our confirmation, if you see, the actual values are, there are actually 10 samples corresponding to class 1, and if you see, the true positives corresponding to that class is again 10. I mean, no false predictions corresponding to class 1 or class setosa. Similarly, if you see, only diagonal matrix are having non-zero values. I mean, all others are zero values, right? If you look at the upper triangle or the lower triangle, meaning there are no false positives or false negatives, right? That's what we can actually understand from a confusion matrix, right? Like we have discussed this confusion matrix in previous lectures. So again, yeah, that's what we could do. So let's actually print this in a like with like in a graphical format. So again, if you see, our accuracy is 1.0, which is actually 100%, right? And then if you see our predicted labels, or the, I mean, if you just look at the confusion matrix, and then only the diagonal matrix, I mean, yeah, it's like it's a diagonal matrix, but only the diagonal values are actually non-zero. I mean, all other triangular values are zero, right? So that's like we could say 100% accuracy from the model. Fine. So you can, now we're actually just having for our visualization, we're actually having our values side by side. If you see, these are our real values in the first column and our predicted values in the second column. And if you see, no mismatching would be there. I mean, say it's hard to see, there are only around 30 samples, I mean 29 30 samples in this data set, right? What if, like, if at all, what if if the test data is around large size? I mean, we can't actually cross verify manually, right? Like, if you see, for the first sample, the real value is versicolor, then we are checking if it is versicolor or not. I mean, the predicted label. So I mean, instead of manually checking it, let's write some enhancement code for it, for checking, for finding out the false predictors, or basically the error rate. So if you see, you'd be getting nothing. I mean, we have got 100% accuracy, right? So there are no false predictions in this case. I mean, if you see, we are sampling our data randomly, right? So if you run this entire code for once again, you'd be again getting one or two false predictions. I mean, that's not in our hands, because our sampling is done randomly, right? Our test set or the train set are, samples are actually done in a random fashion. So that's the reason. So since we have got 100% accuracy, there are no false positives. But in my test run, which I've done earlier, you can see there is one false prediction in this case. I mean, in this part. So the actual label is Virginica, and the prediction is found to be versicolor. This is one false prediction. I mean, it's obvious to you. You can just look it from the screen. But have you ever thought like how does the model perform? Based on the, I mean, changing the number of neighbors corresponding to the model, right? I mean, let's have again quick look at that. What is exactly happening with the model? So if you see, we'll be ranging our neighbors or the n value from 1 to 90. I think like we have assigned our value in the range of 5 inches, right? I mean, if you just look at the, where is that? Yeah. So we have declared it 5 initially. Now let's vary the neighbor values. I mean, even based on the data set also, I mean, we are actually trying to find the optimal k value. Exactly. I mean, precisely speaking. So now let's do that. I mean, how do we find the optimal k value again? We'll be fitting the model for every k value, and then evaluate the error, and with that error, the minimum error will actually correspond to the optimal k value, right? That's obvious. Again, minimal error or the maximum accuracy, anything is fine, right? So if you see many cases, we could see zero error. I mean, most of the values are actually suitable for actually, I mean, fitting on this particular data set. But obviously, iris data set is very popular and small data set. I mean, it's like a sample data set, right? But if you work on real life data, I mean, even complex data with lots of features, because here we have got only four features. I mean, a feature vector size is only four. But if you take some complex data with hundreds of features, then in that case, I mean, this part, the k value would be, I mean, the importance of k value would be, very dominant, in giving out the optimal performance, right? So for better visualization, let's actually plot the error value with the, yeah, if you see, for the corresponding k values, I mean, on the x-axis you have got your k values. I mean, 0 to, if you see only I think it's 5 maybe, or yeah, there's got one, like, point 0 something, some I think, let's see what is exactly happening there. Yeah, so this 0.03, right? So this 0.03 percentage of error is there. So for this particular k value, so if you see most of the k values, we are getting optimal performance. I mean 100% accuracy for all these values where error is 0. So yeah, I mean that's it. I mean if you take any complex data, then then after input your, I mean replace your iris data set with some complex real life data, then you'll be observing some different different patterns in this graph. But exactly, and again if you see I've run a test run actually, then now it's obvious very in from this data set you can look at this on the same iris data set, like because we have already discussed. Since we are doing random sampling, every time we run the same entire code, I mean, output can vary, right? That's what we initially assumed. So if you see in this particular case, when I ran yesterday, for this particular value, I think it's 7, right? So when k value is 7, model is performing the best on the given split of the test data. Okay, we should remember that for that particular random split of test data. I mean, whatever we have used in this particular iteration. So this particular value, we're getting the optimal performance with the kNN classifier. That's what we can say, right? So, so now let's actually get back to the second topic, which is regression. I mean, we are done with classification problems, right? Now let's focus on regression. So again, we shall use the same iris data set, but we'll be predicting, like since we have already discussed, we have got one particular like 4 feature vectors, right? So we'll be predicting one particular feature vector in this case with regression. Like we have got 4 here. So using any 3, we'll be predicting the 4th one using linear regression. So that's what our problem statement. So let's redesign our problem statement from the iris data. So let's do this again. Let's read our iris data into a frame, data frame, which is this variable iris underscore df. So you can see, I mean, or again we shall do that, we shall repeat it again. Let's look at the few sample values. So we have seen this, right? I mean, all of the values in the one single frame, in the data frame. If you look at this one single row, the very first row, all the x values and the class labels are together. So to now so in the earlier case, what did we do? We have actually separated out all the first 4 columns, which are basically our x values or the feature vectors, and the y value, the species value or the class level is our y, right? So which is our ground truths or the labels for each. I mean labels for each sample, right? So in this particular case, what shall we do? We shall be separating out one particular variable, and that will be using for prediction. Okay, yeah, but yeah, input to the linear regression would always be integers, right? So we have actually encoded our class labels as numerical data. That's what you have done. Iris underscore data frame dot species would correspond to this column, right? Dot factorize would do what? Would convert all these string variables into numerical data. So you can see 0, 1, 2 have been assigned to the corresponding classes. So if you see now, just look at this, I mean our input data to the regression model now. So we have got 4 features now, which is our sepal width, petal length and petal width, and obviously the class label. We can also provide class label as well. Even we can get rid of this class label and only input these 3, and then find the 4th value or predict the left out feature, which is sepal length. So I mean it's up to you. So in this case, I'm assuming I'm separating out sepal length and using that as the value to be predicted. It's up to you. You can also predict the class width or petal length or petal width. That's up to you. You can predict any feature. Fine. Similarly, let's look at y values. So you can see these are our first sample values of the y variable, right? What are they? I mean the all the sepal lengths, right? If you see this line, we are actually separating out the sepal lengths and storing the variable y, right? In data frame y actually. So now again, similarly, let's, I mean, you can look at this. Our problem statement is basically predicting sepal lengths, right? That's what you can. It's up to you. You can not only sepal length, but you can also predict anything as of, that's your wish. Again, let's have a 80-20 split. So if you see after 80-20 split, let's look at the size of the train data. So obviously, since we have discussed there are 150 samples, then 80% of it would correspond to the training data, which is 120, right? So there are 120 columns, I mean 120 rows with 4 columns, right? So each sample has got 4 features in it, 4 attributes in it. I mean size of each feature vector. So now let's call our regression linear regression model. So okay, let's import the linear regression model. We are doing what? Again, from the same sklearn or the scikit-learn and linear model, we are importing this particular method, linear regression, which is our regression model. And now let's actually train our model on the data we have got. What is our input data, which is your x train, and your labels y train, right? What are your labels? Your labels are basically the sepal lengths. So using the regression model, you are asking the linear regression model to use this X train. What does X train consist of? All your sepal widths, petal width, and species. These four. Using these four values, we are asking the linear regression model to predict the corresponding sepal length for that model. Let's say, if you input this 3.5, 1.4, 0.2 and setosa or the class label, let's say 0, then the model would predict it as, let's say the corresponding predicted sepal length would be around 4.95 or 5.2 or 5.15, something like that. I mean, if the model is, performing optimally or with 100% accuracy or whatever, it would actually say 5.1 straight away. But yeah, the predicted values, practically would be around with a little bit of error, right? So that error would be around point not something like that. No, I'm just saying it for the namesake. So our predicted values would be around 5.15, 5.2, like that. So let's train our model using this fit method. I mean, just get yourself familiarized with these ADTs and all these corresponding built-in functions. So this dot, what is this? What does it fit do? We are actually fitting the model, itself, and meaning on this particular input data, we are fitting that model. I mean, we are training the model on this particular data, right? So now training is done. So let's actually perform prediction now. So we have got our testing data. So let's predict the model, and you can see, the predicted value is 6.4. Now let's actually calculate the error actually. So we're actually doing what? We are finding 3 kinds of errors. So we should actually import the errors now, right? Uh, Again, from the same from the same package, let's import these two metrics. So now for this, it's same thing, right? For these particular built-in methods, we'll be passing our ground truths and predicted values. So if you see, our absolute error is basically 0.023. So if you see, and our squared error is somewhat less, I mean 0.10, and our root mean squared error is obviously 0.31. I mean the square root of this particular value, right? So I mean not much of an error is there, which is only less than 0.5, which is 0.23, which is basically acceptable practically, right? So again, if you see, for our convenience, let's again have a quick look at the values which are actually predicted. So if you see, for this particular label, I mean for this particular input feature, I mean for this particular sample, the real value is 6.1 and the predicted value is 6.4, which is almost close, right? I mean with an absolute error of 0.3. And again, correspondingly, we'd be getting our squared error or the root squared error. But yeah, if you look at the absolute error, it's 0.306, right? So again, if like you can just have a quick look at the these values correspondingly. For 5.35, we are predicted as 5.35, and the real value is around 5.7. It's almost I mean this amount of error is basically acceptable practically, right? I mean, just for our convenience, we're actually separating out these real values. I mean, making them together in a data frame. So yeah, that's it. So again, no worries. We'll be sharing this entire collab in the common drive. You can again, have a quick look at the, this particular collab file. You can go through it again. If you have any queries, you can get back to us. We'll be discussing them later on.